Okay. Good evening, ladies and gentlemen. We're going to be looking at acids and bases in this lesson. Now, this section is one that you cover in grade 11. Some of the schools, or most of the schools, actually finish it in grade 11. And then in grade 12, most of you are supposed to remember what you've done in the past. And I think some of you struggle just a little bit because it was a very long time ago. And I think particularly with everything being slightly affected by COVID and how everything's working around that, we may find that there is a bit of a situation where it's one of the sections that kind of gets glossed over because everyone says, oh, you did it last year. I also find it's one of the sections that a lot of people struggle with. All right, so before I go any further, can I just double check, can everybody hear me? Thumbs up if you can hear me?
Yes,
Yeah, okay, fantastic, people can hear me. Wonderful. All right. So I apologize to anyone who already knows this section well, but whenever it comes to acids and bases and most other sections, I start with the safe assumption that everybody knows nothing. And we start from the base assumption that you know nothing. And then from there, we build up to hopefully you understanding and knowing a lot more. All right. So we're going to be starting right from the beginning of acids and bases and then working our way through. I am hoping that in this lesson tonight, we will get through what is an acid, what is a base, what makes it strong, what makes it weak, conjugate acid-base pairs, how the strength of the acid-base pairs work, okay? We'll then look at ampholytes, what ampholytes are and how ampholytes work. And then after that, we'll slowly but surely lead into titrations and how to do titration calculations. I am not certain whether tonight we will get all the way to doing calculations on pH, but I'm aiming to if we can. If we don't manage to finish all of the acids and bases work tonight, then we'll continue with whatever we haven't got to when I see you on Thursday. If we manage to get through everything tonight, then on Thursday we will be doing more questions on specifically how to do past paper type questions, okay, as well as some of the nasty stoichiometry questions that come up there. If you haven't revised stoichiometry recently, I did do a lesson on stoichiometry last week, Monday and Wednesday, and you should have access to the YouTube video, or you can contact me if you didn't get it, to just brush up on those if those are your weaker sections. All right, so last thing before we go any further, I'm busy rethinking exactly how we've run this group in terms of people's commitment, people getting involved, and people attending lessons. I will think a little bit further, but I'm very keen to make sure that the people that are on the WhatsApp group are actually the people that are attending or using the lessons. Even if you can't always make it live, that they're at least getting involved and we don't have dead wood that's just hanging around and isn't really benefiting much, but is taking up a space. At this point in time, we're actually across 2 different WhatsApp groups because a WhatsApp group cuts off at 256 people. We've got more than 400 people that have signed up, but not everybody seems to be attending, doing Siavula, doing all of the important things. So I need to make sure that we're getting people that are involved and want to be here. The last thing on Siavula is there is a masterclass that is held every Wednesday that you earn your place in. Now, Siavulas are completely free at the moment, not usually, but at the moment for the whole of lockdown and till the end of this year, it's free. Online platform where you can go and practice science. So what you need to do, and all of you should have this information already, but you go to www.siavula.com and then you click, I think you've got to sign in with your own details, and then you click on a place where it says access code and you put in the 4-word code that I've given you. You type that all in. I know it looks like it doesn't go, like it says A, and a lot of people have said, how do you fit like a 5 or 6-letter word in a space that's got 4 blocks? Just keep typing, it will fit in. And then when you get there, you click on practice, you decide which section you want to do, and you practice. So for this week's masterclass, which will be next week, Wednesday, you need to practice acids and bases. So I will be checking your mastery on that section. You can tell how far your mastery is by the number of stars that have colored in. Every star that colors in, your mastery is going up. And when you've filled all of your stars, then you've got 100% mastery. And fantastic, you're a champion of what you've done. All right, so let's get started with acids and bases. Now, a lot of people from earlier grades know about acids and pH, well, acids and bases from the fact that they're linked to pH, and that some of you guys learned in grade 9, if you touch them and you taste them, they feel different, they taste different. That is a large component of acids and bases, but it isn't what we're going to be focusing on in grade 11 and grade 12 work. I'm going to keep saying 11 and 12 because technically what I'm talking about now is mainly your grade 11 work that's going to be examined in grade 12. Okay, so we need to know that an acid is a proton donor and a base is a proton acceptor. Please note that these are the Lowry-Bronsted definitions of acids and bases. There are other definitions that you can be asked, like the Arrhenius definitions, and some schools even cover the Lewis definitions, but I'm not going to go into either of those because these are way more likely that you're going to get asked about. I find that the biggest problem when we start acids and bases is what a proton is, because a lot of you have learned that an acid is a proton. Well, an acid is a proton donor and a base is a proton acceptor. And then suddenly people start talking about a proton and they use H plus and H3O plus. And most of you have a big problem because your brain is sitting there going, isn't a proton a thing that's found in the nucleus of an atom? And how do these two things link to a proton? So I'm going to start by just quickly discussing what a proton is and why we can call H plus or H3O plus a proton. Okay, this is the most important thing I think we're going to be talking about tonight, because if you don't get this bit, then the entire section on how these protons move means nothing to you, because the entire time you're talking about a proton, you don't actually get what you're talking about. So, Jean-Luc, is there a question already? Okay, please ask it if there is one. So, I'm going to jump in here. Oh, no, let's jump back. Sorry, I'm going to just quickly try and share my screen a little bit more efficiently. So I'm going to share my screen. There we go. And I am going to be talking to you here. I hope everybody can see a periodic table. If you can't, you need to shout. So we're going to be looking at hydrogen. Now, hopefully you all know that you get the atomic number and you get the atomic or mass number. So we've got an atomic number and a mass number. You should all know that your atomic number tells us the number of protons in an atom. It also technically tells us the number of electrons if it's neutral, okay? But it usually, protons is the guaranteed number. Electrons can change if we have an ion. You also have your mass. Now, this mass comes from all of the particles inside the atom that give rise to either, well, mass. So it'll be your protons plus your neutrons. That means that if we look at hydrogen, which we can write as H11, hydrogen from the top number, which is the mass number, tells us that our number of protons, which I call P plus the number of neutrons must be 1. And the bottom number over here tells me that my number of protons is 1. So what I can deduce from this is inside a hydrogen atom, I have got 1 proton. If it's a hydrogen atom, we could also say that it's got 1 electron because it's neutral at this point. And we have got no neutrons. Okay, so if I were to draw this, there's a proton in the center and there's an electron on the outside. Now, we're not talking about H. Everything here has been talking about H. We're going to be talking about H plus. That means, because it's charged, that it is an ion. It is an atom that has lost or gained electrons. And in this case, the fact that it's a plus, it tells us that it has lost an electron. Okay, so if we have a proton and an electron, and we remove the electron, we can see that H plus is literally what we call a naked proton. It's a proton with no electron, no neutron, therefore it is just a proton. Now, a lot of people think they've got this idea, and then I follow with my next example, and I say, okay, cool, so lithium. Is Li plus a proton? Here's the question, is Li plus a proton? And I'm not going to embarrass any of you this evening. The answer is no, lithium is not a proton, okay? Because if we look at our numbers, it's got a mass of 7 and an atomic number of 3, which means that we have got 3 protons, 4 neutrons, and if it's neutral, we'd originally have had 3 electrons. The fact that it has got a plus charge tells me we've lost one, so it's only 2 electrons. But the point is that is not the same as just 1 proton. So it isn't the positive charge that makes it a proton. It's the fact that once you have an atom that had a proton and an electron, and you took away the electron, you have literally got a proton left. So that is why we refer to H plus as being a proton, because it is. All right. Can I quickly just check before I go any further that everybody understood this idea of what a proton is? Okay, brilliant. Now put down hands. I've already seen a couple of thumbs. So that's fantastic. My next question, probably more importantly, is who never understood that this is what a proton is? Is there anyone here, if you give me a thumbs up here, where you had an idea before that a proton was H plus, but your brain never made the link to why a proton was H plus? Okay. There are not so many of you, so that's fantastic. Well done on making that connection before. But I just find that it's so important because otherwise you're talking about something and you don't actually understand what it is that you're talking about. So our next discussion is to why this H plus is our proton and why we sometimes refer to it as H3O plus. So I'm now going back to grade 11 again. If we have just our proton, which is H plus, okay, so I'm going to please ask if there are any questions, rather keep them for when I ask in between, but I'm just quickly going to go back and say the reason that this is a proton is that a hydrogen atom originally had 1 proton and 1 electron. When we turned it into an H plus ion, it lost the electron, so all that's left is a proton. It's literally a naked nucleus with a plus proton in the middle and absolutely nothing else. Okay, so if we looked at the atomic number and the mass number, that told us the number of protons, neutrons, electrons. We take away the 1 electron because it forms an ion, which is a charged atom, and that makes it our H plus. The reason it's H3O plus is the H plus will often combine with water. And in all things when we're dealing with acids and bases, we're dealing with aqueous solutions. Water's around, so if you've got a water and an H plus joins with the water, you form H3O plus, and this is known as the hydronium ion. Please note, it does have other names. It is also known as the oxonium ion, but I've only ever actually heard one other school refer to it as an oxonium ion. So an oxonium ion is kind of very outdated terminology, but it isn't incorrect. It's just another name for it. So what we're going to be looking at now is how an acid acts as an acid and how a base acts as a base. So please, if you excuse me, I'm going to be talking exclusively about acids for a while and then exclusively about bases. I know that I'm going a step back, but I know that there are also some grade 11 students who are watching tonight who've only just begun this section. So I want to make sure that I kind of sweep from the back and make sure that everybody gets complete understanding. Bear with me if you're smart and you already know this. All right. So we've already mentioned that an acid is a proton donor. So I'm going to start off by giving you a couple of names of different acids. You need to know these. If we start talking about sulfuric acid, you can't be sitting there going, what's the formula? You need to know it. So I'm going to put the acids down and I'm putting them in a very specific order. Okay, not super specific, but the ones at the top and the ones at the bottom are different. So we have H2SO4, we have HCl, and we have HNO3. Those I typically put at the top because these are what we refer to as our strong acids. Okay, so that was sulfuric acid, hydrochloric acid, and nitric acid. Okay, then the slightly weaker acids, we have, I'm not going to get through the whole list because there are a lot of them. Okay, so I may put down, I just got to think, H2CO3, which is carbonic acid. Carbonic acid is what we get in fizzy carbonated cool drinks. H3PO4, phosphoric acid. Then linking to your organic chemistry, CH3COOH, which is our acetic acid or ethanoic acid or vinegar. And then lastly, COOH2, which is our oxalic acid. Okay, there are many other acids that I haven't put on this list, but I think these are the ones that I want to focus on quite a large amount. So just a quick thing for those of you on your organic chemistry, acetic acid is CH3COOH. Please note, even though we've gone and said that an acid is a proton donor, only this H is acidic. These protons here are not technically protons. They're hydrogen atoms that are strongly bonded to carbon, and they're not going anywhere. So this acetic acid will lose this proton, and when it does, whatever's left here will look like this. It'll be CH3, C double bond O, O, and then it's got a minus because it didn't just lose an H, it lost an H and a plus. So you must remember, whenever you take a proton away from something, you don't just take away the hydrogen, you take away the hydrogen and the charge. Okay, so this was acetic acid. It's also known as ethanoic, yes, it is. It's also known as ethanoic acid, which is vinegar. And this over here is either acetate or ethanoate. Depending on whether you viewed it as originally being acetic acid, then it's acetate. And if you viewed it as being ethanoic acid, then it's ethanoate. Okay. The next important thing is this oxalic acid is a C double bond O, O, H, double bond O, O, H. And because it's got two carboxyl groups from a carboxylic acid, remember that's that functional group, it's actually got two protons that it can lose. So when it loses those protons, this one will go and this one will go. Okay, oxalic acid means that once we produce our product afterwards, it looks like this, and it's got two negatives. Okay, so you'd often write this as COO2 minus. That is known as oxalate. Okay, and this would be written as CH3COO minus. Okay, so those are just some of the slightly difficult ones. Now, I mentioned right at the beginning, I'm losing my train of thought, but trying to keep it, that these are strong acids. Please note, these are weaker acids. So when we speak about an acid is a proton donor, which means that it's going to give away an H+. When it gives away an H+, our acid will actually form a base. Okay, I'm going to quickly repeat that. I'll in fact even write it down. When an acid acts as an acid by giving away a proton, it forms a base. But it's not just any base, it forms what we call a conjugate base. So a conjugate base, conjugate means joined, and it's a base. So I've unfortunately got my poor stylus here. I'm just going to quickly borrow one of my children. Jamesy, can you come here? Just stand over there so that they can see your hand. Okay, I have a proton. My pen is my proton. That makes me an acid because I can lose this. My son James, whose hand you can see here, does not have a proton, but he has a space to hold a proton. That means he's a base. If I act as an acid and I give away my proton, I now have a space to accept a proton, so I can act as a base. James, who originally didn't have a proton, was a base, accepted the proton. He now has a proton, which means that he is now an acid. We'll cover the base becoming a conjugate acid. Thank you. So the idea that we've got here is when an acid gives away a proton, it forms its conjugate base. If acetic acid is my acid, then that means that the acetate is what we call my conjugate base. Okay? if we start with the oxalic acid, which I did over here with its 2 protons as the acid, its conjugate base is the oxalate. All right, so I hope you get the idea that if something had a proton to give away, it was an acid. As soon as it gives away that proton, it's now got a space to accept a proton, which means it becomes a base. I want to quickly, before I leave this page, discuss with you what strong and weak acids are. So when we talk about an acid giving away its proton to form a base, we often talk about acids ionizing. So an acid will ionize by giving its proton to water, okay, or to something else, but we're talking here about it ionizing. Okay, the question here was, when does it lose its H plus proton? The answer is when it acts as an acid. And I'm going to discuss now why things will act more readily as an acid or not. Okay, so can I quickly check, has everybody taken a screenshot of anything that they want to? I want to just quickly clear myself a little bit of space. I am going to get to answering the questions in just a second. Okay, so there's a good question here from Nasia about sulfuric acid and the spelling. I always love spelling sulfuric acid with a PH, but technically they changed it to an F in the year that I was born. And for years I refused to spell it with an F, but F is technically correct and it's been around for longer than I've been alive. So I decided recently that I have to put my gripe with bad spelling because certain people in the world can't spell, and then they decide that that's how we're all going to spell badly. I believe that it should be a PH, but I've kind of succumbed to the fact that I can make it an F. Both are perfectly correct. Neither will ever get you penalized. Okay, so I want to talk about what makes something a strong acid versus a weak acid. Strong acids ionize completely in solution to create or to generate, you can choose your word, a high concentration of, I'm not certain if someone was asking a question there, you need to speak up if you were. So to generate a high concentration of H3O plus ions, hydronium ions. So what that means is if you've got a strong acid, when it gets put in water, it will immediately give away its protons. We don't even have to technically say when it gets put in water. As soon as it has an opportunity to lose those protons, it will lose them, okay? So if we were to have HNO3 and we react it with water, immediately what will happen is that this proton will get lost and the proton will be given to H2O. Please, you don't write that little arrow that I drew there. It's not necessary. So what happens when the H plus joins with the H2O is we get H3O plus, and what's left over here is the NO3. Please remember it's an NO3, and because it lost an H and a plus, it's NO3 minus. So when nitric acid acts as an acid, it will produce a nitrate ion, always. So sulfuric acid will produce a sulfate. This is just for you to know, that's what it produces. Hydrochloric acid will produce a chloride. Nitric acid will produce a nitrate. Carbonic acid will produce a carbonate. Phosphoric acid will produce a phosphate. Acetic acid will produce acetate. And oxalic acid will produce oxalate. All right, so what this means when we say it will ionize completely is that every last HNO3 will break apart to form NO3 minus and H3O plus. None of them will stay together. They ionize completely, break apart completely, okay? If we are instead dealing with a weak acid, weak acids ionize partially in solution to generate or to create, I lost that there, to generate a low concentration of H3O plus ions. So what this means is that if I have my CH3COOH and I react it with water, it is going to act as an acid and it is going to lose its H+. That H+ will join with the water to form H3O+. Okay. We will also have what's left once we've lost our H+, which is CH3COO-. But unlike the previous situation where every last HNO3 split apart the second it was in solution, here some of it will remain together. So some will remain together, some will split apart, and then as we learned in chemical equilibrium, they will rejoin and they'll swap. So what you'll find is that there's a certain percentage of CH3COOH where the H sticks with its base, and somewhere it splits. And then it's an equilibrium. So some splits, some comes back, some splits, some comes back. But it isn't like this massive splitting and never seeing each other again that we find with our acids. So you need to know which acids are strong. As a typical rule, it's these three, although recently in past exam papers, they have put in other specific things and they'll tell you that they're strong, or they'll give you equilibrium constants. If you remember what equilibrium constants were, there's an equilibrium constant called Ka, which is actually the ratio of these two ions. And remember, if you think about it, it's concentration of that times concentration of that over concentration of this, and we leave out water completely because water is a liquid. Please, if you didn't understand what I just said, you don't have to stress about it. Ka doesn't come up very often, but if we end up being given a very large value for Ka, we can say that an acid is strong even if it isn't one of those three. So a lot of teachers teach that those are the only three, and I know I've often taught that way. And then last year they put in something that wasn't one of those three. And suddenly we as teachers had, well, I was sitting there going, well, what do I go with? Do I go with it isn't a typical strong acid, or that it is? So they can be more than that. There was a quick question. Are acid-base reactions reversible? Completely. That is why we have things that donate protons and then reaccept. I would definitely view all of them as being reversible, but it's also a case of how much they, don't ever say this word want, but however much they want to be reversed. So if something is a strong acid, that reaction is not particularly reversible because it doesn't want its proton back. Okay, it wants to lose it, it doesn't want to accept it again. Whereas if you've got a weak acid, it would rather willingly lose a proton and then have the proton come back. If you remember what I said, Beth, about the conjugate base. So an acid gives away its proton to form a conjugate base. That conjugate base can just as easily reaccept a proton. Okay, so what would be a very large Ka value? I think anything above, like, you see, this is where it gets really tricky. I'd say if you're dealing with a Ka value that's in the hundreds or thousands, definitely strong, okay? But there isn't actually a clear cutoff value that I've ever learned. All right, just quickly going to write down the Ka value. Please, if you didn't do the class on equilibrium constants, go and watch the video before you come back with the question here. So this is the Ka value specific to this example. Ka will equal products, concentration of NO3 minus, times by concentration of H3O plus. They're both aqueous, so I can put them in, over the concentration of HNO3, which is aqueous, and then this here will be liquid, so we assume it's 1 and we leave it off. Now what you should find, and the reason why the Ka value is so high, is that if I tell you that all of this turns into products, then this should actually be almost 0. In fact, we'd like to say that it's 0, which means that we can almost get to the point where your Ka value is undefined. Okay, got a huge number divided by 0, and that gives rise to a very large Ka. Whereas here, with this example, my Ka value would be the concentration of CH3COO minus times by the concentration of H3O plus over the concentration of CH3COOH. And because not all of this broke down, we'll have probably an even split or even distribution of these two. So your Ka values usually for a weak acid would be less than 1. They can be a little bit bigger, but it depends. Also with the strong to weak acid, it's a scale. It isn't this thing where there's this dividing line and those are strong and those are weak. Even within the weak acids, you get stronger and weaker acids. All right. Can I quickly just check? I'm about to clear everything that I've got here. So I'm going to quickly stop sharing for a second. Can I quickly check that everybody is still with me and understanding? Okay. I know that there's some big concepts that we've dealt with here. I think some of you already understood them. Some of you are getting a good revision on them. Okay. So those are our acids and how our acids react. Now, before I go much further, I'm going to quickly clear my whiteboard altogether. And I'm going to talk to you now about what we mean when we talk about ionization. So ionization refers specifically to a reaction where something reacts with something else. So in this case with the ionization, it's the reaction of an acid with water. So I looked at the example already where I showed you what happened with nitric acid. I'm now going to show you what happens with sulfuric acid. So if we react sulfuric acid with water, we will once again produce H3O+, hydronium ions. Now, the problem, although it's not really a problem, the problem with sulfuric acid is that it is what we call diprotic. Diprotic means it can give off 2 protons. And when it comes to ionization, we have to appreciate that it can give them off one at a time or both together. I find that if I'm ever asked to give a reaction for ionization, I only ever take off 1 proton at a time. If it says complete ionization, then I'll give off both. Okay, so if I'm asked for just the ionization, I will take off 1 H and a plus. That means that I'm left with HSO4 minus. This is the first ionization step. Reaction of the acid with the water to produce, this is our conjugate base. Please note its name is bisulfate. There you go, I'm back with the pH. Or you could call it hydrogen sulfate. Okay, it has a special name. Okay, that is the first step here. If we were to do the second ionization step, we'd then take our HSO4 that has a HSO4 minus that's already lost a proton and would react it with water again. This time it would lose the H and another plus, and we're left with SO4 2 minus and water. Sorry, H3O plus, sorry, the water's there. Okay, so this is the first and the second step. It is also possible if we choose to, and this is where it gets really tricky in an exam because nobody tells you the answer and they don't tell you if they want just the one or both. So unless they're very clear, I'm very cheeky and I do first step, second step, and the overall just in case anybody wanted anything and nobody can accuse me of not doing it. So HSO4 can also react with 2 waters to produce SO4 2 minus and 2 H3O pluses. Okay, so that is our ionization. For any ionization reaction, just remember it's acid plus water gives you your conjugate base plus hydronium, and all that's happened is an H has gone and a plus has gone. Now please, with regards to this, if this started off as a minus and I lose another plus, it becomes 2 minus. That's how we often work out the charges that we get on our conjugate bases. All right, so that is an idea as to how ionization works. The last thing that I just quickly wanted to mention or bring up at this point is the difference between concentration or concentrated and dilute. Okay, I can see their questions. I'm just quickly going to jump there. Will they tell us when an acid is diprotic, or is it something you should know? It's something you should know. So to give you a quick list, I can quickly jot down some, but it isn't an absolute rule. H2SO4 is diprotic. Acetic acid is diprotic. Carbonic acid is diprotic. Sulfurous acid is diprotic, but it's weak. That's sulfurous acid. Then we can deal with something called polyprotic. Monoprotic, we don't usually say, but monoprotic gives off 1 proton. Diprotic gives off 2 protons. Polyprotic gives off 3 protons. Okay. And then just one thing with regards to the definitions of monoprotic, diprotic, and triprotic before I come back to concentration is you've got to say, so if I were asked for the definition of diprotic acid, I would say that it donates 2 protons, very key word, per molecule. If you leave that bit off, nobody cares, no marks, okay? So per molecule of acid. So the idea here is each of these can give off 2 protons per molecule, and if it's triprotic, it gives off 3. Sometimes we just say polyprotic for more than 3. So it can donate 2 protons per molecule of acid. Whoa, lots of questions. Okay. Ma'am, is it not diprotic if it has H2 in it? It's not always the rule, because if you remember when I looked at the example of acetic acid, CH3COOH, those first H's were not acidic, so they didn't count. All right? Will we lose marks if we don't include the phase symbols? All right. Nasia, to be dead honest with you, we don't normally penalize marks if you're missing state symbols, but it's a good idea to put them in. At the moment, though, I'm making sure that you understand the concepts more than the phases. So we could here quite comfortably have said over here, but then this also gets tricky. The sulfuric acid here, I'm going to have to pretend that if that's a liquid, this should technically be aqueous, but if it's aqueous, it's already in. So it gets a bit tricky with our state symbols, and I don't always fuss too much about them. All right. Okay, and I haven't yet gone to acid-base pairs, so I'm going to come back to them. But over here, this is a conjugate base. Just to quickly answer the question, in this step, it's an acid, but we'll get to ampholytes just now. Okay, so pause, don't run ahead of me. Okay, we're getting there. So I want to finish up what I was talking about over here with concentration. We spoke about acids that are strong and weak. Now, a lot of people confuse strong and weak with dilute and concentrated. I can have an acid that is a strong acid, and I can dilute it down, and it's still a strong acid. So strength of the acid, whether it's strong or weak, isn't something that can change. Okay, it's a property of what the formula is and how that acid behaves. Dilute and concentrated has to do with the amount of water. So if something is concentrated, there is a high ratio of acid to water. And if something is dilute, there is a low ratio of acid to water. So if you think about something like your Oros at home, you can have concentrate, and then to make it dilute, you simply add water. The fact that you add water to an acid isn't suddenly going to make it eager to lose its protons or eager to hold on to its protons. That's built into what the substance is. Okay. All right. I hope everybody's okay with this. Please quickly just take a screenshot, because I'm ready to move on to bases. Okay. So I'm going to clear everything, and we're going to move on to bases. Now I'm going to go through bases rather quickly, because bases have many properties that are very similar in terms of strong, weak, dilute, concentrated, etc., that we've already discussed in quite a lot of detail when we looked at acids. So our strong bases, we can assume that any strong base, or our strong bases, are group 1, 2, and 3, as in groups on your periodic table, metal hydroxides. So that means I can assume here that sodium hydroxide, lithium hydroxide, calcium hydroxide, okay, I'm only listing a few here, aluminium hydroxide, although aluminium hydroxide gets to be a bit borderline, because it's not quite as soluble in water as you'd like. So it tends to be your alkali metal hydroxides that we'd regard as being strong bases. If we look at our weaker bases include the metal oxides, all transition metal, so that's from the main body of your periodic table, the transition metal hydroxides, all metal carbonates, I should probably say most metal carbonates, okay, metal carbonates, metal oxides, and then lastly, ammonia. Ammonia is a very important one to know, because it's very likely to come up will be raised. Now, I'm not going to write this out because it'll take me time, but if we were to talk about a strong base dissociates completely, I may have spelled that terribly, don't worry about it, in solution to generate a high concentration of hydroxide ions. A weak base will dissociate only partially in solution to generate a low concentration of hydroxide ions. Now you need to be fully aware of the fact that this is your hydroxide ion. Okay, so your hydroxide ion is your OH minus. If you, instead of using the word dissociate, use the word ionize, there isn't going to be a penalty. But you cannot say that an acid dissociates. Dissociate means to split apart. When an acid reacts with water, there's a chemical reaction. It isn't just a splitting, which is why you may not do that. So if we were to deal with a dissociation here, we can say sodium hydroxide will split apart to form Na+, which is aqueous, and OH minus, which is aqueous. And we don't need to worry about the fact that it just split apart and it didn't react with water. We've got hydroxide ions. Now, if you remember our definition, which I hope you do, because it wasn't very long ago of a base, the base is a proton acceptor. And the reason that bases are proton acceptors, if they form the hydroxide ions, is that the OH minus will combine or pick up the H, we technically say H3O plus, we don't like to call it just H plus on its own, and that will form two water molecules. So here, this was a proton acceptor. It accepted the H plus. All right, so that is why we say that it's a proton acceptor. Ammonia does not produce a hydroxide ion, but the way that ammonia acts as a proton acceptor is that NH3 picks up an H plus and forms NH4 plus. So this over here is ammonia, and this over here is ammonium. Okay, so what you hopefully can see over here is this acts as a base because it accepts the proton. It gains an extra H, so you'll see we're going from 3 H's to 4 H's, and there's an overall plus because it gained the charge as well. All right, does this make sense to everybody? Okay, quickly take a screenshot if you need to. Okay, Tristan, is there a question?
Yes, ma'am. Did you say that weak bases dissociate partially in low concentration? Okay, cool, perfect, thanks.
So it's just the opposite here. This would be weak, this would be partially. Even if you say not completely, you'd probably get away with it, and it would create a low concentration of hydronium ions. We can also say that this creates H3O plus if we want to. I'll quickly show you. If we instead did this here and we showed ammonia reacting with water, we can show that it forms NH4 plus, and the leftovers of the water that remains behind gives me OH minus. So it does technically also produce a hydroxide ion if we react it with water. Okay.
Thank you.
Okay, so quick question, just going back. Ka and Kc are the same thing. They're calculated exactly the same way. It's just that the A says that it's a dissociation constant of an acid, not a dissociation constant based on specific concentration. So it's kind of like a specialized Kc value. All right. So far, we've dealt with a bunch of things about what makes it an acid and a base, what makes it monoprotic, diprotic, triprotic, what makes it strong, and what makes it weak. I'm now going to jump back to the idea of how conjugate acid-base pairs work. So I'm going to quickly clear everything from here, and then we're going to get started. I know we're going a little bit slowly, but I think, can I quickly just actually stop and check? Who's happy with the pace that we're going at? Thumbs up if this is a decent enough pace and you're not feeling very slowed down. More than half of you. Sorry, everybody else. That's cool. All right. I never know where to paste things, so I've got to just check. I'd rather not lose anybody than race too far ahead. Okay. If I sadly lose you because you're too bright, well, that's something I'm sure you can deal with. All right. So we're now going to be looking at conjugate acid base. All right, I need to be very careful when I do this because I often pick examples that I don't want to do later. So if I have got sodium hydroxide and I reacted with nitric acid, there is a rule that you learned way back when you were in grade 9 possibly, which says that an acid plus a base goes to give you a salt plus water. Now, the definition of what a salt is actually gets really tricky, and it usually isn't taught to you. The best version that I've had of a definition of a salt says that it is formed when the hydrogen of an acid is replaced with a metal. Which sounds very confusing, but it's actually not that tricky. So when it comes to forming salts, you've got to be smart. If you look at your acid, take whatever is left once it's lost the H, and that is what we're talking about, what's left. So the hydrogen of an atom is replaced with a metal. We are taking the NO3 because the hydrogen is being replaced. So our rule here, as I said, is nitric acid forms a nitrate. Then what we do is we look at the metal from our base, and the metal from our base tells me that this is sodium nitrate. Please make sure that you check your ions and your oxidation numbers. That's Na plus NO3 minus. So they're 1 to 1, so it's Na, NO3, and then we're left afterwards with water. Okay? So this is our base, this is our acid, that's our salt, that's our water. You need to be able to work out what the salt is, and you look at the end part of your acid, that will always give you the anion, okay, the negative ion of your salt, and the metal at the front will always give you the cation. The only exception is that sometimes if your salt has ammonium in it, then it usually didn't come from that, it came from ammonia. So I tend to teach that it came from ammonia. There are other versions of this, but I prefer to make it ammonia rather than ammonium hydroxide, which is just a disaster. I don't go down ammonium hydroxide route. If your teacher does and you understand it, perfect. I'm not teaching it. Okay, so what we're now going to be talking about is the strength of conjugate acids and bases and what we get. So when sodium hydroxide acts as a base, it picks up a proton. When the hydroxide picks up a proton, what we end up producing is water. So this we call our base. What we produce when the base acts as a base and it gains a proton, this is what we call our conjugate acid. Okay? When the acid acts as a base and loses a proton, we're left with the NO3 minus, which makes this my conjugate base. Okay, so the acid acting as an acid, the acid acting as an acid produces a conjugate base, and the base produces a conjugate acid. And our rule when we form these is that a weak acid produces a strong conjugate. Please write it out in full in exam. A weak acid produces a strong conjugate base, and a strong acid produces a weak conjugate base. So the idea with your conjugate acid base pairs is that if you have something that is weak, it will produce a strong. Same applies for bases. A weak base produces a strong conjugate acid, and a strong base produces a weak conjugate acid. Now, the logic behind this comes from And I often give chemicals personalities. I see them as having personalities, and I can see who's mean and who's nasty and who's greedy and all of those things. Don't ever write it in an exam, though. It'll get you into trouble because atoms don't have personalities. But I want you to imagine, when you imagine over here a weak acid doesn't want to lose its proton. So I always have a mental picture of a little toddler who has to give a birthday present to somebody else that they don't want to give. They actually want to keep it for themselves. Okay, so if you've got something that you don't really want to give away, you're going to be a weak base. And if by chance you had an opportunity, once you'd given away that present, to be the first person to play it, look at it, do whatever, then you are a strong conjugate base. You're a willing receiver. Okay, so if something is weak at giving, it's going to be exceptionally good at taking back. Okay. If something, on the other hand, is a strong acid doesn't want that thing. It does not want that proton. When it gives away the proton, if you try to give the proton back, it's really cool. You can keep it. Keep the proton. We do not want the proton. Strong acid doesn't want a proton back. So it's always a good idea, if you imagine in your head that something is a strong acid, wants to get rid of it. Then imagine, if you want to get rid of it, do you want it back? Okay. Similarly, for a base. If something is a weak base, it wasn't a very keen or willing receiver. So it's like, okay, fine, I'll take it. I don't know quite what I'll give it to someone else. Okay. So if something is a weak base, it's going to be a very strong acid. Didn't want to accept, very good to donate. All right. So this idea of conjugate acid-base pairs is something you need to go through. Now, linking to conjugate acid-base pairs is the section on hydrolysis. Now, I'm not going to be covering the section on hydrolysis today very deliberately. Hydrolysis is a very complicated section that is only worth 2 or 3 marks in your exam maximum. So what I'm going to do is, you have an opportunity in the masterclass. I promise I'm going to go over hydrolysis, but you've got to earn your way to be there. I will post the video of the hydrolysis section when I've done it afterwards if you weren't there. So you won't miss out on it. You can always go and watch it and catch it up. But I'm not going to be going through it now because it'll probably take the majority of our time that's left. Okay. And it's not necessarily even going to be asked. So I will cover it, but I'm not going to cover it right now. Okay. I hope everybody's good with this. All right, ladies and gentlemen, we've reached about halfway through the lesson. So I'm going to quickly ask everyone to quickly stand up and stretch your legs so that you don't fall asleep on me. And then we can continue with the rest of what you need to know. All right, so can everybody just quickly stand up, stretch arms and legs. Take a bit of a break if you need to. It's only going to be a short while, but it's just to make sure that you get comfortable and you do not fall asleep completely on me. All right. Okay. So we're going to continue from here. What I would like to look at now is, I want to quickly look at what an amphilyte is, and then we're going to jump straight into titrations, because I know that a large number of the schools are going back, and the first thing that you're looking at is titrations, and I want to make sure that you know what we're talking about when we talk about titrations. Hopefully you found that you already know most of the basic things that we're going to get started with. All right, so I'm going to share my screen, and we're going to get straight into this. All right, so the first thing is, what is an amphilyte? Now, spelled it wrong. There's a PH. So an amphilyte is also known as an amphiprotic substance. So it's the same thing. And what it is it's effectively a substance that can act as either an acid or a base. Okay, so in order for something to be an amphilyte, it has a couple of physical properties that it needs to have. First of all, in order to act as an acid, it needs to have hydrogen. If it doesn't have hydrogen as part of the formula, it's got no chance of doing that. The second thing is, in order to act as a base, it needs to be able to accept a proton. And I've found, by looking at all of the amphilytes, that the one thing that I find you need to have in order for something to act as a base is that it must either have a neutral charge or it must be negatively charged. Okay, so we tend to find that substances that are amphiprotic or amphiolites, I'm just going to quickly correct that before it bugs me, tend to be substances that either are neutral or negative. So our first example is water. Water is an amphiolite. Another example is HCO3 minus. So you'll see that it could technically turn into H2CO3, or it could turn into CO3 minus, depending on if it gains or loses a proton by acting as an acid or a base. In this case, water can turn into H3O plus, or it can turn into OH minus, okay? H2PO4, in fact, there are two versions here that can react. So here we could get H3PO4, or we can get HPO4 2 minus. So you can see here that this is your amphiolite. And if it gains a proton, that's what it becomes. And if it loses a proton, that's what it becomes. So there are a large number of different examples, and I'm just quickly listing the most common ones that tend to come up. But please make sure that in an exam, before you say that something is an amphiolite, you check that it is actually acting as an amphiolite. There was a question that came up, I think it was last year or the year before, where they had both HCO3 minus and H2O in one reaction. And you were asked to identify which substance acts as an amphiolite. And water, although it is an amphiolite, didn't act as an amphiolite in that particular reaction, and it wasn't even entertained as a discussion. It wasn't somebody going, oh wait, but they realized it was an amphiolite and we should be nice and give them a mark. There was no discussion. It wasn't even raised. If it didn't act as an amphiolite, if it didn't in one reaction show that it lost a proton, and another reaction show that it gained a proton, you could not say that it was your amphiolite. All right, so amphiolites are often very good. There's a scientific term, we don't usually teach this, but I'm just teaching because it's important. They're very good buffers. So what we can do is we can put them in a solution where we don't want the pH to change very much. Inside your body, this HCO3 minus is responsible for making sure that you don't die. It makes sure that your body's pH does not become too acidic or too basic. And as soon as your body has too much acid, it then quickly acts as a base and removes that acid. If your body becomes too basic, it acts as an acid and it does the opposite. So in your body, the HCO3 minus makes sure that your body's pH stays very constant. If your body's pH changes by more than 0.1 pH units, you're not sick, you're dead. All right, so that was what I needed to quickly cover with amphiolites. Now, I wanted to chat to all of you about titrations today. This is the last thing that we're going to be touching on. Yes, Kiesma?
Ma'am?
Yes?
For the example with the water and the HCO3 minus,
Yes.
Could you give maybe the equation that was used in to show how you could distinguish it?
I think it was one where I can't actually recall exactly, but I think it was something like you had H2CO3. So it's the most recent November paper, this year or last year. It literally was one that I was expecting to come up in discussion and it didn't. And then it went to form and then this, okay, I can remember what it was. This reacted with water to produce, oh my goodness, it produced HCO3 minus, okay? And then the HCO3 minus reacted with, and H3O plus, okay? And then this reacted with water again to produce CO3 2 minus and H3O plus, okay? So it did the same reaction twice. But if you look carefully, this is your acid, this is your acid, this is your base, and this is still your base. Whereas here, this becomes your conjugate base. Okay, so here we could show that it was a base in this reaction and it was an acid in that reaction. And therefore it could react as either an acid or a base. Whereas in this case, the water was always a base. Does that make sense?
Yes, ma'am. Thank you.
Doing it as an amphiolite, you had to see that it acted as an acid and a base there, but it was always a base in the other one. Okay, that was very much not titrations. So I'm going to quickly clear everything here and then rewrite titrations. Okay, so the first thing is most of you should have done a titration already. And the whole purpose of a titration is actually to determine the concentration of a solution that we don't know the concentration. Okay, so we determine the concentration of a solution. Now, what we have to do in a titration is we need something called a standard solution. They almost always ask you the definition of a standard solution, so it's important you know this. So you need a standard solution, which is a solution of known concentration. So usually when we make a standard solution, we make it very accurately, and you hopefully know this from your stoichiometry section. So we would have a specific mass of solute that we would carefully dissolve in a beaker filled with water. I'll make that blue so that you can see, because water's blue. Okay, so it's made up in a beaker. And so we put the mass into a certain, actually this isn't even a volume, this is just water. This is deionized or distilled water. We take the mass, we have weighed it out very accurately, we add it to the water, we take a spatula or a glass rod and we stir it. And then what we do is we carefully put it into, and I'm drawing this beautifully, what we call a volumetric flask. I'll show you the proper pictures just now. And what makes a volumetric flask so special is that it's got the exact volume measured out perfectly. There's a thin little line around the top that tells you exactly where you've got to go. And what you do is you pour the solution, you take out the stopper first, and then you pour the solution in, and it probably comes to somewhere here. We mix it until it's dissolved, we pour it in here. And then what we do is we carefully drip, 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 fill this whole thing up until it's exactly on the mark. In fact, it isn't just exactly on the mark. We draw a line, we've got to make sure that the bottom of the meniscus falls on the line. So you all hopefully know what a meniscus is. Okay, the meniscus is the curving of a liquid surface. So it kind of curves and it rises just gently around the edges in there. So we measure from the bottom of the meniscus and we make sure that we know an exact volume. And for most experiments, the volumetric flask that we use is exactly 250 centimeters cubed, which we would convert to 2.5. What's happening with my brain there? We convert it to 0.25 decimeters cubed. So by us knowing the exact mass, we know the exact number of moles. And because we've filled it to exactly the right volume, we don't, please, this is very important, we don't fill it to the 250 and then add the solute, because the solute takes up a volume and it'll rise too high and the water level will increase, well, the total solution level will increase too high. So that is how you make a standard solution. So usually you need to know that a volumetric flask is not for a titration. A volumetric flask is to make a standard solution. In addition to that, you use a glass stirrer, a beaker, a scale. Remember, we need a scale here to determine the mass, and then the volumetric flask. Please note, we usually don't store chemicals inside a volumetric flask. It's just to make up our standard solution. And there's also one last key word. When we make something up, we must make sure that our eye is at exactly the right level to view the bottom of the meniscus to avoid the error of parallax. The error of parallax comes in when you are looking at something but from a slightly different angle. Just to give you a bad example of an error of parallax, whenever I'm in the passenger seat and my husband's driving, we've got a speedometer where it's a needle and it's raised slightly from the dashboard. But from my side-on perspective, it always looks like it's going faster than it really is. So I'm often one of those backseat drivers that sits there going, but you're going too fast. And my husband is adamant that he is not going too fast, but it's an error of parallax where your view, the because there's a gap between the two differs. So if you looked at this from above or below, this applies to all the readings that you do in titrations, you would see a reading that's too high or too low because you're not looking directly on. All right, so the first thing that you need for a titration is a standard solution. In an exam, they may make you make up the standard solution, or they may just present you with a lovely, here's a standard solution, here's its concentration, this is what it's doing. You need to be prepared for both, and you need to be prepared to calculate the concentration by saying that the concentration is either the number of moles over volume, or that the concentration is equal to M over MV, where this is your capital M, which is your molar mass. Please note, in order to work out a standard solution, you must know its identity. You can't have a standard solution and not know what acids or base it is. So it must have a known identity because you need to be able to work out its molar mass. Okay, so that's the starting point of a titration. Then we're going to talk quickly about the actual titration. I'm going to draw my drawings through this, and I'm going to show you what they really look like. So at the end, you'll be like, ah, that's what she was talking about. Okay, so the next thing that we do is with regards to our calculations in a titration. Now, with the titration, you have a long, skinny thing with a bulb on the top. Now, different schools use different bulbs. I have a very cool one like this, but some of them have ones that are a little bit more linear and have a roller down the side, and they do the same thing. So this, believe it or not, is my version of a pipette. Okay, a pipette, no end bit. This is my version of a pipette. Okay, and this is what we call a filler bulb. They have fancier names like Pro Pipette. And what this pipette does is it has a line on it, and you can suck up exactly 25 centimeters cubed of solution. All right, I don't know if I'm going to be able to show an example of a standard solution, but I'll see if I can record one and send it to everybody when I'm actually in the lab. Okay, so I'm not going to do it right now. I'll explain it, and hopefully I'll be able to get it to you. What we then do is we use the pipette to put a certain quantity, usually the 25 centimeters cubed of solution, into what we call a conical flask. I'm covering all of the terminology here because you never know what they're going to examine you on. The conical flask is deliberately shaped with curved sides so that if anything splashes in here, that the splashes run down. Okay. Okay, so what you would do is you would pipette this quantity into usually 3 or 4 conical flasks in one go. And remember, in this pipette, you could either put in the acid or the base. I tend to prefer to usually put my base and pipette it into my conical flask because I tend to find that the bases clog up the burette. Sodium hydroxide particularly makes such a mess, it crystallizes, and then you can't move your burette at all. All right, so that would be your base in one. If our base went into our conical flask, what also goes into the conical flask will be an indicator. And an indicator is any chemical substance that changes color depending on whether it's in an acid or a base. Okay, that's the one side of this. On the other side of this, we have an even longer thing called a burette. Okay, and a burette usually has a little tap on the side. We usually use a funnel when we fill up our burette because we don't want to make a mess. So we've got a funnel, we got a burette, and usually because our burette doesn't keep itself standing upright, our burette gets clamped into place, and we usually, I know my drawing is awful at the moment, but we usually have a retort stand. Please retort, I have seen some terrible spellings of that. This is a retort stand, and then connected to it, we usually have a boss, and this little bit over here is called a clamp. So quite often they'll talk about retort stand, boss, and clamp. Okay, and what's going to happen, in fact, is this burette has got a little tap at the bottom and liquid can run through it. We're going to put the conical flask underneath here, and we're going to put it on a white tile. Specifically white, because that way we can see the color change. Now, it doesn't actually have to be a white tile. I found that years ago I actually went and got white tiles from CTM, and we use them all, and a white piece of paper works just as effectively. The white is there so that you can see the color change. All right, I cannot tell you which labels you're likely to be asked. Most of these are asked in your practical that you do for matric, so it's worthwhile knowing all of them. Burette, Pipette, Conical Flask, and volumetric flask, I'd say, are the most important. All right, now what we're going to do here is, if you think about this, we know the volume and we know what's in here. So we can actually work out how many moles we've added. And the important thing here is to realize that concentration is number of moles over volume. So number of moles is concentration multiplied by volume. Okay, very important. So if we have something that we know its concentration because it was the standard solution, and we know the volume because we carefully measured it out here, okay, we can know how many moles there are. All right. So what we're going to do here is we're going to try and get the number of moles of acid and base to be equal to each other. And we'll know that they're equal to each other when the indicator changes color. All right. Also, because we know exactly what volume, okay, please remember, very important technical thing, they're not going to examine you on it though. The funnel is there when you pour it in, then you take the funnel out, otherwise the funnel drips and chemists freak out. We know what the initial volume was on the burette, and once we've run it down to the point where it changes, where the indicator changes color, we can know what volume we added here. So we've got a situation where we know this volume and we know this volume. We also know the ratio of the moles of our acid to our base. So remember, if this was a base that went in here, we would typically go and put an acid in here. We'd have an acid reacting with the base till the point where they neutralize each other. When we get that color change on the indicator, we know that they've neutralized each other. So I just quickly want to show you, so I'm going to quickly share a screen across, because I did actually go and find this. Okay, so I went and looked for a video. This is not me, it's just a random person with brown hair. Okay, and I'm not even going to show you the whole video. I just want to show you the setup. So there is the funnel. Can everybody, sorry, the funnel's over there. There's just a beaker. Over here, we've got a burette. It's got a tap over there. And in fact, whichever way the long end of the tap goes, there is a hole through the middle of here that goes in the same direction. So if that hole goes in the same direction, liquid can pour through. So if my thing goes this way, then the hole goes this way and nothing can go through it. If it goes that way, liquid can flow down. Okay, so you can see there's a scale there, and we would pour the liquid through here until it changes color. Now I'm going to quickly push play here so that you can see the actual process. You're not going to be able to hear the sound. Okay, I want to just quickly show you what the titration process looks like. So there you're going to open, that's called a stopcock. You're going to open the stopcock. Hopefully at some point she will, and the liquid will run through there. So I just found this one where I like the way it went. And you can see over there, there's a color change at the bottom. That's because we've got phenolphthalein in the bottom, and it's our indicator which is changing color. So she's going to pour this in slowly until we get a color change which corresponds not to the clear or to the pink, but our end point is actually on a beautiful kind of orangey peachy color, which is viewed as being an in-between color between the two colors that we've got here. So that is going to be our end point that we achieve, and she's going to keep swiveling around. It's also a very unusual thing to do with titration because your hands don't quite work the normal way. So if you're right-handed, you actually do it with your left, and she's going to keep adding here until she reaches her end point, which is when it goes. So we started with clear. Let me just quickly see. Sorry, I'm jumping ahead. So usually we do our first one very rough. Okay, there we go. I don't know if you can see over here. I think she might already have reached it. That looks almost pale pink there. She lets more go in. It's going to go drop, drop, drop one at a time. There we go. And I think she's right here at the end point now, and she knows that it's gone pink. She's going to swirl it up. Okay. So at that point, that was actually the end point. I'd have viewed the end point as being one step earlier than that, where it was still that pale pink color. That for me is the end point here. I look for it being pale pink, not to have been over titrated to a point where it's fully pink. All right, so that just gives you an idea as to how we do the various titration things. Most of you should have done a titration at some point at school. All right, so I'm going to stop sharing just quickly. All right, and now I'm going to go back. Does anyone have any questions just before I go into how to do the calculations? Okay. All right. Okay. So what is the endpoint? The endpoint, just for the record, is the point at which your indicator changes color. And what point that is depends on what indicator you use. I'm going to discuss how you choose your indicators just now and what colors they go just now. So the indicator that was used here was phenolphthalein, spelled phenolphthalein. Okay. So, but I'll come back to all of that just now. For now, I want to focus on being able to get you to the calculations, because what the color change was and what the indicator was is only going to be one mark. It's not going to be enough to make it worthwhile if you can't do the calculations. So our equation that we use here, I've got my formula sheet because I always get confused as to which way around it is, I think is CAVA over CBVB is equal to NA over NB. And it's very important that you know what all of these letters stand for. So Ca is the concentration of the acid, and it will be measured in moles per decimeter cubed. Va is the volume of the acid, and in this particular case, your volume of your acid can actually be in either centimeters cubed or decimeters cubed. I strongly advise that you convert it to decimeters cubed, because centimeters cubed cannot be used for your pH calculations. And if you get too comfortable using the wrong units, then we get into trouble later. Cb is the concentration of base, and Vb is the volume of the base. Na and Nb are probably the most misunderstood things here. These are actually your mole ratios from the balanced chemical equation. So if I were to deal with an example, which is what you'll probably deal with, where we have sodium hydroxide, okay, and let's make this just HCl, nice and straightforward. Our equation is NaOH plus HCl goes to give us NaCl plus H2O. If we look at this equation, it's 1 to 1 to 1 to 1. This 1 is your NB, number of moles of base in the balanced equation. This one is your Na, number of moles of acid. So depending on what our acid and base are that we're asked, we're going to use different ratios. Okay, and then other than that, you plug them in. If you remember right at the beginning, I told you the whole purpose of this is to determine the concentration of an unknown solution. So you will know those two. One will come from the pipette, one will come from your burette, which we actually call the titra value, okay? So those two will be known. One of these two will be a standard solution, so you know its concentration, and the mole ratio you'll know from the balanced chemical equation. So you should, at this point, be able to fish out every single one of those values. All right. So what I thought we'd finish off with today, before I go into the stuff that you've just got to learn, is an exam type question on this particular setup. So I think we've done enough to do most of the questions on a particular exam paper that I found, and I thought I'd quickly just share it with you, and then we could go through it together and make sure that everybody understands all of the questions. So this particular question is going to take us through most of an exam paper. It fortunately is taking us through a paper, the kind that you really do pray that you get, but sadly, I don't think you're ever going to get. Okay, so we can wish and hope and pray, but it's unlikely to be the case. All right, so I'm going to share my screen, not that screen. Where are we? Sorry. I'm going to share my screen. Sorry, it took me to whiteboard and that wasn't what I wanted. And here's the exam question. All right. So I hope that everybody can see this. This question, just in case you're wondering, comes from the May-June 2015 paper. I think the reason that this is such an easy question paper is that acids and bases, if I recall correctly, was pulled out of the syllabus around about 2008. So if you do any papers between 2008 and 2014, you'll notice acids and bases aren't in them. This, I think, may have been the first paper where acids and bases was put back, which may explain why it's slightly easier than you'd normally get. So question 7 says anhydrous oxalic acid. That word anhydrous just means it doesn't have waters of crystallization, and therefore it's that exact formula. Don't panic anything further than that. It's an example of an acid that can donate 2 protons and thus ionizes in 2 steps as represented by the equations below. So this is where we're dealing with a acid, and it gives off 1 proton and then gives it off another one. So question 7.1.1, write down one word for the underlined phrase in the above sentence. Does anyone know the answer? You're welcome to shout out. What do we call an acid that can donate 2 protons?
A diprotic acid.
Yay! Thank you. I'm sure that many of you got that right. It is a diprotic acid. I must be honest, I want to write in here per molecule, because there's so many people who get penalized when they don't write per molecule. The examiner definitely should put it in. All right, and the formula of the 2 bases in this reaction, you can identify what our 2 bases are. Okay, anyone? Okay, I'm going to give you a heads up. This is oxalic acid, so this is an acid. That means that water is a base. So my formula means I have to write H2O. I may not get away with anything else. And then I'm going to cheat. I'm going to work out the conjugate. I could put in this as being a base again, but it's not going to get many marks. I write water and water and hope that they go, oh, wow, you figured out it was water twice. So what we need to do here is we need to figure if that is an acid, loses a proton. So that is my conjugate base. Okay, this is my conjugate acid, but I'm forgetting what I was doing because I only needed to work out what the base was. So the formula of the other base was HCOO2 minus. Okay, then it says, what is the formula of the substance that acts as an amphiolite in reactions 1 and 2? Who can give me an answer for that, bearing in mind that I did almost the exact same thing with you recently? Any idea? Oh my goodness. Okay, so over here, the HCO, so that substance, it even gets tricky for me to name. I kind of want to call it hydrogen oxalate, which probably is the right answer. Over here, it acts as an acid again. So it acted as an acid and a base. It's the substance that acts as an amphiolite. Fortunately, they deliberately said formula because they don't want you to get tongue-tied about what its name is. It's HCOO brackets 2 minus. There we go. Give a reason why oxalic acid is a weak acid. I find with this question, you guys get so funny because you kind of try to explain why it's a weak acid instead of just putting the definition of what makes an acid weak. Okay, there's another question. Isn't the second base the other one? Well, you could also have said that this is also a base. Okay, so technically when it asks for the 2 bases, you could say that it's, sorry, that one, or that one. 100% correct, all 3 of those are bases. So COO2 2 minus, oh, I lie, you are 100% correct. I missed that. It was in reaction 2. I missed that bit about reaction 2. You are so smart. So I had to actually focus on this base and this base. This one doesn't count because it said reaction 2. Oh my goodness, I got caught by that. I'm pretty sure most people would get caught by that. So please be very, very careful. I wasn't smart. One of the rules I always tell my students is when you see something bolded, slow down. There's a catch. And I didn't read that that was bolded and I didn't slow down and I tripped. Okay, so carrying on again. 7.2, give a reason why oxalic acid is a weak acid. A lot of people get very worked about trying to explain why it's a weak acid. In order to say it's a weak acid, you can just simply say that it only ionizes partially in solution to generate a low concentration of H3O+. Okay, so your definition, I probably shouldn't put the brackets around there because I've already said the word concentration, but that is your explanation. A reason why something is strong is because it ionizes completely. A reason why something is weak is because it ionizes only partially. You don't need to explain why it ionizes completely or only partially. All right, so I'm going to quickly clear this. I hope you've all taken any screenshots that you need to. Well done. I didn't actually pay attention to who it was, but well done to the person who picked up that. That's a very important thing to pick up, and that's telling me you're going to get fantastic marks for reading in the exam as well. It sounds, sorry, that sounded a little bit sarcastic. Reading is vitally important in the exam. You really need to be able to read. So well done on picking that up. All right, next question. Okay. A standard solution of COOH2, that's our oxalic acid, is of concentration 0.2 moles per decimeter cubed, is prepared by dissolving a certain amount of COOH2 in water in a 250 centimeter cube volumetric flask. Calculate the mass of COOH2 needed to prepare the standard solution. So I'm going to work backwards here. I'm going to say C is equal to M over MV. And I'm going to do this very quickly because I want to make sure that we finish in the next 5 minutes. Please don't disappear. I find that people always disappear at the end and you miss out on the important things that we haven't yet got to, like the last question. So I did not need to put in units here. I don't recommend you put in units as long as they're in the right values. We're looking for the mass. The molar mass of COOH2 is going to be 12 times 2 plus 4 times 16 plus 2 times 1. Please note there are 2 carbons, there are 4 oxygens, and there are 2 hydrogens. So it's 12 times 2 plus 4 times 16 plus 2, which gives me a molar mass of 90 grams per mole. So this will be 90. The volume, since it's 250 centimeters cubed, please don't forget to convert it to decimeters cubed. So to get M as the subject of my formula, I must be careful. Everything gets multiplied together. So it's 0.2 times 90 times 0.25. 0.2 times 90 times 0.25 gives me an answer that I need exactly 4,5 grams. All right. And I think that that's 4 free marks. A lot of the grade 11s, this is grade 11 work here, and you'd be able to go 1 mark. I don't even know where they get 4 in here, 2, and then it probably was for conversion there, or substitute. It's either substitution both sides or the conversion. Now, quickly take a screenshot if you need to, because the last question is the one that I wanted to get to with all of you today. As I said earlier, this is the kind of question you pray for in an exam. The last question is talking about a titration. So it says here, during a titration, 25 centimeters cubed of the standard solution of COOH2 prepared in the question is neutralized. Now I've actually got to go back up a screen quickly because I didn't write down what its concentration was, and that concentration is important. Wrong question, just give me a second. The concentration was 0.2. So I need to just quickly make sure that I've written down all of the things that I needed to know here. I needed to know that it's 0.2 moles per decimeter cubed. And then I needed to know that there was 25 centimeters cubed of it, that is COOH2. I'm writing down a piece of paper so that I can use it later. And it's neutralized by sodium hydroxide. All right. So I unfortunately don't have tons of space here to work in. So I'm just going to quickly see if I can zoom out a little bit so that I give myself a little bit of side space. There we go. All right. So please just wait until the end so that you get a solution to this. Promise I'm going to finish in the next 2 to 3 minutes. So we're going to use the equation. Sorry, it says use the Burette readings to calculate the concentration, and that's what we're going to do here. So if the Burette reading starts over here, I hope you all realize that that's 38 and that's 39, and there are 5 divisions here. So I would call this 38.8 centimeters cubed. And over here, that's 2 and that's 3, so this would be 2.8. Please always look at what it is. Don't assume that you can read it, because a lot of people get confused here and they'd say that's 3.2 and it's wrong. So I can now go straight in and say CAVA over CBVB. is equal to Na over Nb. Okay. If I look at this, the concentration of the acid we were given before as being 0.2. We know that because it was our standard solution. We were also told that we use 25 centimeters cubed of it. So I'm going to make this 0.025 because I'm putting it in as decimeters cubed. If you put it in centimeters cubed, you still get the same answer. We are looking for the concentration of sodium hydroxide. I hope you all remember that square brackets is the symbol for concentration. And the volume of base we've just worked out here as being 38.8 minus 2.8. The Na comes from my mole ratio. So Na is over there, which is 1. Nb is over there, which is 2. So I can jump in here. My number of moles of acid is 1. My number of moles of base is 2. From there, I can calculate the concentration of my unknown solution. Now, I don't want to rush this because I find that when I rush things right at the end of a lesson, I always seem to mess up. So I'm just going to quickly do this here. So I get an answer of 5 times 10 to the negative 3. I'm going to cross multiply. That was that times that. Here, the 1 comes down to the bottom. The 2 goes up to the top. So that went there. That went there. I'm going to keep my value here of 38.8 minus 2.8 to give me 36. And the Na goes up to here. NaOH, there we go. So if I have 5 times 10 to the negative 3, I hope people at home are doing this to check me, and I times it by 2, please remember that's a times by 2, not a squared, and I divide it by 36, I get a very small answer. I know why I get a very small answer. I've already made my mistake. I did this as being 25, okay? This should also have been divided by 1,000. So that should have been 36 divided by 1,000. If you ever get a concentration that's really small, you need to make sure that you ask yourself why it's so small. So if it is, there's a problem. So here we've got 5 times 10 to the negative 3 times 2 divided by 0.036. And my concentration then that I get for sodium hydroxide is, sorry, my pen's going funny now, is 0.2787778. So I'm going to make it 0.28 moles per decimeter cubed. All right, I'm just quickly going to erase that last bit and then I'm going to chat to everybody. So there we go. All right, so that is the final answer. I'm pretty willing to bet that most of you have suddenly gone, there we go, shouldn't be in decimeters cubed. So you see the problem here is if you're going to use a unit, make sure that you stick with the same units. After all of that, I changed that to decimeters cubed and left that there. So this technically should have divided by 1,000 to convert correctly. And then that gets our concentration done. All right, please quickly take a screenshot if you need to. All right, and I'm going to clear all of the drawings and I'm going to stop sharing. All right. Ladies and gentlemen, I hope that you enjoyed that. We're going to be continuing when I see you again on Thursday by looking at some of the more detailed approaches, how you decide what indicator you use, as well as pH calculations.